Kia ora koutou. Here are questions 1, C and D from this year's Level 2 Algebra paper. So this question is one where I think when you first look at it, it looks really, really hard and you're going, what is this doing in the exam? But most of it is completely fine as long as you go slowly. So what I recommend you do when you get a question like this is you make sure that you read the whole way through the question first and think about how you're going to start before you kind of just dive in. So we're told that a calendar can be presented in the following way, where each day is given a number from 1 to 365. And this is the start of a year's calendar, right? So you can see it starts at day 1 and it goes on and on. Notice that we've got the 7 columns for the days of the week. And so here is just a 4x4 square on the calendar, right? So reading on a bit, so we've got something going on here with the colours. So we've got orange, yellow, and blue. I'll get rid of my blue ones there. Okay, so Jo draws a 4x4 square on the calendar to check a claim that she heard. And she's drawn that 4x4 square here. But the claim is that the sums of the diagonally opposite corners are always the same, no matter where you make your square. In other words, where you add up the numbers in the orange corners, it's the same as when you add the numbers in the blue corners. So you can see that in this particular example, 21 and 39 add up to give us 60, and 18 and 42 add to give us 60. So she wonders if the claim will still be true no matter where she starts the square, so she begins an investigation using algebra. I have some recommendations for Jo on maybe she should find some other hobbies or find some more interesting maths problems, but anyway, let's keep going. So they've given you a big clue here, and they've given you a grid in the paper that has got those colours in it. So I'm going to use that for mine. If they hadn't given that to you, I would have drawn something pretty similar. So just drawing something like this so that we can keep track. So let's write in what do we know about the rest of what's going into that square. So it's important here that we've looked at the picture because we've got 7 columns going across, right? So we can see that this number here, this 18, when we get to the next Monday, it's going to be that number plus 7 and then that number plus 7. And that helps us a lot here. So here in the top rows of these ones here, we've got a plus 1, a plus 2, and we've got a plus 3. Now it's important that we write that out because we're going to use the blue corners later on. And then if we keep going, we know that this line here is 7 below the one above. So here we've got a plus 7, and we'd have a plus 8. I'm not bothering with the yellow stuff because I'm not going to use that in the questions. But this next one would be a plus 14, and then the blue one will be a plus 21, and that will be a plus 22, a plus 23, and this will be a plus 24. Something weird happening with my... Sorry about that, guys. Okay, sorry, so PowerPoint just glitched slightly. Or OneNote. So just filling this in here, this orange one here will be a plus 24. Right, and that makes sense because this one, the blue one here is 3 weeks further on than the first row. So the first thing we've got to do is to use algebra to prove that no matter where we've drawn that 4x4 square, that the sum of the orange corners must be the same as the sum of the blue corners. So the orange will be a plus 24, which gives me 2a plus 24. And the sum of the blue corners is a plus 21 plus a plus 3, which is equal to 2a plus 24, which is equal to the orange corner sum. So we've done that first part. Now let's look at the next one. Jo wonders about the product of the diagonally opposite corners. Could they be the same? Use algebra to prove that it's not possible to draw any 4x4 square for which the products are the same. So we've done most of the work for this because we know what's in those 4 corners. Right, so the products. What we're asking is when is A times a plus 24 equal to a plus 3 times a plus 21. Now that's because the orange ones the A and the A plus 24. So this is when it's the orange equal to the blue. So we've got a quadratic here. We're going to expand it out. And on the left-hand side, we get a squared plus 24a. And then here we get a squared plus 24a plus 3 times 21, which is 63. So solving that gives me 0 is equal to 63. So that's telling me that there are no solutions, right, because this does not make sense. So there is no starting point. That makes this true, or that gives us the diagonally opposite product is equal, or some words like that. Okay, I haven't seen the schedule yet because it's not out, but just, you know, some kind of communication that what we've done shows that there are no solutions, so there's no place where this will happen. Okay, what's next? Right, so then we've got the third part of this question, which is definitely a little bit more abstract, but it's not too bad if you've thought about the structure. So will it always be true that the sum of the orange corners, so we're back to the sum, not the product, the sum of the orange corners must be the same as the sum of the blue corners, regardless of where she draws the rectangle and what the size and shape of that rectangle is. So we've got to use some algebra to support our answer. But if you want to get a feel for this, you could start by let's just draw that rectangle there, and let's have a look. So, oh, sorry, I didn't change the pen. Here we've got 5 and 15, which is 20, and here we've got 8 and 12, and that's working with a 4 by 2. Let's try another one here. So let's do this rectangle here. And you can see, if you look at those diagonal corners, you've got 40 plus 70 is 110, which is the same as 42 plus 68. So what we have to do here is to generalize it to use algebra to support our answer. And we've got an m by n rectangle. So we're going to do m rows like this, and n columns like this. Now, it doesn't matter if you do this the other way around. I'm sure they're going to be quite forgiving of that. Let's look at what our square would look like. So we've got A here, and if we've got m rows and n columns, what I know for sure is that the starting point, the number underneath the starting point will be A plus 7. And then how many times am I going to have that happen? Well, if I've got m rows, that means that I'm going to have A. I've got, so this is row 1, row 2, row 3, up to row m. So here I'm going to have A plus 7 times m minus 1, right? If we think about that, we've got A times A here, A plus 7 here, and we've got A plus 2 times 7 here, right? And that's in row 3. So in the last row, the mth row, I've got my starting point A, and I've got m minus 1 times 7. Now let's look at this end of it down here. What's this end point going to be here? Well, this is A, and out here, this is going to be A plus 1, A plus 2 in here, and I've got n columns, so this end one will be A plus n minus 1. If you're having trouble seeing why it's n minus 1, go up to this one here, this blue one that I've done here, and see how we started with 40. This has got 3 columns, and that last number is 40, not 40 plus 3, but 40 plus 2, right? And in this one here, I've got 4 columns across here. This number here, the 8, is my first number plus 3, not plus 4. Okay, and then the last thing we've got to do here is we're going to have, down the bottom, we're going to have A plus 7 times m minus 1. So we've got our starting point here, plus n minus 1. Now let's look at the sum of the blue. blue diagonals. Which ones are the blue? Which ones are the orange? Right. So the blue ones are these ones here. So the blue sum will be a plus n minus 1 plus a plus 7 times m minus 1. That's this one and this one. Let's clean that up now. So that's 2a plus n minus 1 plus 7m minus 7. So 2a plus n plus 7m minus 8. What we want to do is end up with that expression for the next one. So the orange sum is this one and this one. So it's a plus 7 times m minus 1 plus n minus 1, which gives me 2a plus 7m minus 7 plus n minus 1, which is 2a plus n plus 7m minus 8. Okay, so we've got that, and we've got that, and they're exactly the same. So what have we shown? Well, we've shown that, yes, it is always true that the sums are the same. So there you go. Now, I think that that question actually in some ways is much easier than the excellence questions that we usually see in the Level 2 algebra paper. It's just a different way of thinking about it. The maths in there, like the solving and stuff, is something that you could have done back in year 10, but you just have to be confident with thinking about what's m and what's n and how does it link up to the diagram that you've drawn. So one thing that you'll see over and over is that doing a good diagram and being able to use the diagram is a skill that really, really helps with problem solving. Thanks for watching. If you've got any questions about that one, feel free to either email me or leave me a comment.